Now we will give some examples of regular submanifolds as promised, but first we want to make a remark. So if we apply the regular level set theorem that we just talked about in the previous video, if we apply that theorem to the case when the smooth function f is from a manifold, our manifold M, to the real number, so it's a smooth value, a real valued functions on M, and by translation by C, we can just assume that this is fiber over 0. Then we have a situation similar to linear algebra. In linear algebra, the zero set of any linear equation, or say equivalently any linear functional, is a subspace. And each such equation cut down the dimension of the vector space by at most 1. So in our case here, each such function here also cut down the dimension of the manifold by 1. And that's how we get regular submanifolds, by keep cutting the manifolds with these equations. However, remember, don't forget the important condition that 0 has to be a regular value of this map. Okay, so let's look at 4 examples. The first 2 examples are gonna be regular submanifolds of R3, and the 2 other examples will be regular submanifolds of GL and R. Now we claim that the unit sphere x squared plus y squared plus 1 in R3 is a regular submanifold. Why is that? Well, we can view it as the fiber over 0 of the smooth function. Now that's not enough. We need to check that 0 is not a critical value. In other words, for every point P here in the fiber, we need to check that the Jacobian of f at P has full rank 1. Now the Jacobian of f is just gonna be given by 2x, 2y, 2z. So the only critical point of the Jacobian of f is the origin, but the origin does not lie on the sphere. So the sphere does not contain any critical point of this. And so 0 is indeed a regular value, and thus the sphere, being the fiber over a regular value, must be a regular submanifold. Now in example 2, we can add to this, we will look at the intersection between this sphere and the plane with normal vector 1, 1, 1. The plane going through the origin with normal vector 1, 1, 1. Then in that case, we can view that intersection as the fiber over the map to R2. Now it's not a map to R1 anymore, it's a map to R2, given by these 2 functions, right? This is the intersection of the 0 sets of these 2 functions. And the Jacobian of this map is this, given by this matrix. These are the column. So this has rank 1 if and only if this row is a multiple of this row, and in that case it will not lie in this fiber. So this fiber again does not contain any critical point, and so it must be a regular submanifold. Another way to find the critical points is that the critical point should be where all the 2 by 2 minors of this vanish, and we can solve for the critical point. Now in the case of the general linear groups, to show that these groups, the special linear group and the orthogonal groups, are regular submanifolds, what we need to observe is that they are cut out by the following map. They are fiber of the following map. So for the special linear group, it's fiber of the determinant map, right? And then for the orthogonal group, that's fiber of this map, which sends every matrix A to A transpose A, because the orthogonal groups are exactly the matrix A consists of exactly the matrix A, such that A transpose A is equal to identity. To show that these are regular submanifolds, we would need to show that these points are regular value. So in other words, we will need to compute the critical points of both of these maps, and then show that these fibers do not contain any of those critical points. But that is that computation is a bit more involved, so we'll do that in a separate video. Now we just want to make a final remark. We want to deduce the dimension of these as manifolds from the regular level set theorem. So what should the dimension of SL and be? Well, here R is of dimension 1, so then SL and R should be of codimension 1 in here. So the dimension of SL and R is just n squared minus 1. Now for this map here, we have to take the domain to be the symmetric matrices, otherwise we don't get this as a regular value. In other words, otherwise the map on tangent spaces might not be surjective. So if this is a symmetric matrices, then the codimension of this orthogonal group inside GLN must be equal to the dimension of this. And what's the dimension of this? Well, symmetric matrices are only determined by the entries in its lower triangle. We can count the number of entries here. It's like summing 1 plus 2 plus 3 all the way up to n, so that's going to be n times n plus 1 over 2. So the dimension of On is going to be n squared minus this, and so it's going to be n squared minus n over 2. Alright, so those are some examples of regular submanifolds. Next we'll show why regular submanifolds and embedded submanifolds are basically the same thing.